Right. So today will be the first day of this multi-wavelength school. Day one will be dedicated to optical and infrared astronomy, to be followed by a radio day and an X-ray day. I will only briefly touch on the other two wavelength domains today. And I'll focus on optical and infrared photometry and spectroscopy. So there'll be no polarimetry or interferometry appearing in my contribution today. Let me start off with three introductory slides. One point I want to make is much of astronomy nowadays is time domain astronomy. And here's an example of an event that has been in the news even before it happened, and it has been in the news multiple times before it even happened. The next nova explosion of T Coronae Borealis was predicted to happen last year and then earlier this year. We're talking about an object, a star, then changing 10 magnitudes in brightness. That's a factor 10,000, but it hasn't happened yet. So maybe it'll happen later this year, and optical and infrared and radio and X-ray astronomers would be rather excited the day this really gets going. We'll talk more about time domain later today. I want to talk briefly about the origin of the radiation for all three domains. I just mentioned T Coronae Borealis. There is a SCD shown, a spectral energy distribution for it shown on the top left panel here. You see the black points fitted by sort of a thick blue line. This is pretty much just thermal radiation from that single temperature photosphere of the star. Most of the light you see here is in the infrared because we are looking at a red giant. And then there is this, further below, there's this light blue line. I wonder, can people see my mouse if I drag it along here?
Yes.
Yes.
Thank you. This is supposed to be an accretion disk around a compact white dwarf that forms a binary companion here. And so as you go into the UV, the thermal radiation from this accretion disk then actually dominates over the star. And especially when the accretion disk goes into a height state, becomes brighter, it just pushes up this contribution and lifts the UV here. And in the nova outbreak, we would see this essentially going totally through the roof, expected in the next few months. Now, the shape of this spectrum is very different from the pure Planck shape, Planck single black body shape of the red giant. And that's just because we're not looking at a single temperature, but we are looking at the accretion disk having a temperature profile from extremely hot, emitting X-rays, in fact, on the innermost edges, to relatively cool and emitting infrared on its outer edges. And so over on the right, I'm now showing not an X-ray binary like the one down here, but something similar, in fact, an AGN, which is, if you want, a version of an X-ray binary in very, very large. The difference is the compact body is not just a stellar mass white dwarf or black hole, but it is a supermassive black hole. The accretion disk is correspondingly large and luminous. And then the companion isn't just one star, but actually the black hole would be surrounded by an entire host galaxy with billions of stars. So you get a similar situation that you have the combination of the thermal emission from a accretion disk with a temperature profile that would be sitting here, dominating the near infrared, the optical, and the near UV. You have, in addition, contributions from the starlight, from the sum of their photospheres from the host galaxies. And whether you can see one or the other really depends on the contrast, because AGN come in a range of contrasts. In some cases, the accretion disk is less than 1% of the starlight, and unless you use special tricks, you don't realize there's an AGN embedded in this galaxy. Or it could be the opposite extreme. You could have an ultraluminous quasar, and you're totally dominated by seeing the accretion disk emission. And if you want to see the photospheric emission from the host galaxy stars, you have to do special tricks to isolate that. Now over to the higher energies, we have the X-rays emitted by hot corona associated with the inner parts of the accretion disk. That's also mostly thermal radiation and also Compton effect going on here. And then finally, on the radio side, you have free emission, or in fact, mostly you have synchrotron radiation coming from jets associated with the AGN. And we'll focus now on this inner part here, which is almost exclusively thermal emission, at least when we talk about the continuum. Of course, there's also emission lines. People who work on galaxies more generally know, why did this go back? Know the emission lines that are typical for galaxy spectra. We also find them in the spectra of AGN. They are then associated both with the galaxy itself, if it has star formation, and also these are associated with gas that's ionized by the hard radiation of the AGN itself. And we can tell the difference between the two because the two different types of ionizing radiation, very hard radiation from an AGN, or softer radiation coming from the young stars in star-forming regions, they would create different ratios in the strength of different emission lines, which have, because the different species have basically different ionization thresholds. All right, moving on. So we've just talked about a little introduction here, and I want to go into the nitty-gritty details of some data and how we're treating the data to get science out of this. So I'll show you in a moment some example images, some example light curves when you want to do time domain astronomy, some example spectra. Then we'll try to do photometry and talk about what can go wrong, what are the systematics, what are the noise levels that we're dealing with, and what different types of photometry do we actually do for different purposes. This means aperture photometry or PSF photometry, and then the hardest of them all, photometry for extended sources. And I'll say not too much about that, just because you could have a workshop on that topic entirely for a whole week, and we wouldn't make much progress on all the other nice things we want to do. Then I'll talk about the spectroscopy and how we extract spectra from raw data sets, and finish off with complications on calibration and standard stars. There'll then be a separate section, a separate talk where I'll talk about some data resources that we have available from the Australian side for collaborative projects, and get into some nitty-gritty problems with those. Okay, so that's what we're gonna do. Here we have some example images. They are all taken from the ANU SkyMapper telescope for convenience, because I know how to find the images. An important thing to differentiate is whether a survey that scans the sky is looking to create an image atlas, or whether it's a survey for transients. Now, when you're just trying to create an image of the sky, you see images such as the 6 images on the top left. What objects are you going to pick up or overlook? Well-separated sources you typically pick up as separate sources, and they can have separate entries in a catalog that you produce from these images. But very often you have the situation that you have blended sources, and you will typically not differentiate them unless you specifically go looking for that, and you make a bespoke effort that very often the producers of the survey do not do for you. Now, transient surveys are different. I mean, very often they look for supernovae, for example. That's one of the most popular types of transients. And they are then usually seen projected against their host galaxies. So you always have a situation of a blended object. And you know, good examples you see on the top right. In these two panels, you see a supernova here in the crosshair on top of the host galaxy. Again, here's the supernova, and then there's the host galaxy. And if you just did a source extraction on images like that, you wouldn't pick up the supernova. You would maybe not even notice the supernova is gone if you observe this a second time and you create a second timestamp for the catalog entry, because it's still one object as much as it was over here. It's only when you subtract those images, you see the rare things that actually have changed. Everything that's static then gets removed, and what's left over is just the images of the objects that are transient. And if you do transient surveys, this kind of difference imaging and difference photometry is absolutely essential. Moving on, I show you some example light curves, and you will now see examples for difference light curves on the left and absolute light curves on the right. So here on the left, I'm showing 6 different AGN, and what you notice on the flux axis is that this seems to be centered on 0. Here on the bottom are 3 AGN that we consider non-variable AGN. They're actually type 2 AGNs. So you kind of measure always the same brightness, and it sits at a 0 here because what has happened is that a reference image was subtracted. The 0 means not no flux, it means no change in the flux. And then on the top here, you see variable AGN, and they can have sometimes more and sometimes less than the average flux. So hence you get both positive and negative values here. With the supernova happening in an otherwise static galaxy, the galaxy is usually at the 0 level. And when the event happens, it only has positive flux. It can't have negative flux because it's just an add-on. And the galaxy sets the reference level here. Now, the 2 light curves on the right show you the total flux of an object. In this case, these are point source quasars at any of these epochs when they were observed. Down here, we actually see a nice microlensing event that lasts for a little over 5 years. And up there, you just see a generally variable, stochastically variable quasar. Example spectra. These are all taken from the ANU 2.3 meter telescope, with one exception of an infrared extension to a spectrum that comes from the SOAR telescope. And I'm just contrasting a couple of extreme cases here, just to illustrate 2 basic points. If you have enough exposure time or bright sources, your spectra will have excellent quality. So the noise in this spectrum is actually smaller than the thickness of the plotted line, with the exception of some special spots here in the infrared part of the spectrum where it's really hard because of our atmosphere making the sky very bright. So this is an example of an extremely high quality spectrum. Everything you see is signal from the object. And then here on the right, we have another quasar spectrum with a lower signal to noise, and especially at the redder end of the spectrum where our own atmosphere's night sky emission dominates and is notoriously hard to subtract out. You get all of these noise features appearing, and it gets hard to differentiate what's really from the quasar and what's an artifact of bad background subtraction. Now, not everything that looks spiky and wiggly like this is a bad background subtraction. On the bottom right, we see again a quasar spectrum, and here at the red end, we see all of these night sky emission line residuals from a bad subtraction. But you take a quasar and you look at the blue end of the spectrum. If it is at redshifts greater than about 2, you see similar features, qualitatively similar looking features, but they are actually true astrophysical signal. These are intergalactic clouds, basically imprinting hundreds of thin, narrow Lyman alpha absorption lines onto the spectrum. So this is truth, whereas that is just a bad subtraction. All right. Something that happens not too often, but often enough to be a concern for people who work not just on their 3 favorite objects, but on lots of objects in the sky, is that we get blending of sources. We have only a finite resolution in our observations based on the seeing in the atmosphere, or maybe based on the size of a fiber through which we collect light for a spectrum. And sometimes you get blending of sources. So here is a source that looks like a bright star. And if we magnify this, we see there is, yes, a bright object here, and then there is actually a galaxy around there. We can check the Gaia entries for this. And yes, one thing has a high proper motion and a parallax, and it is a star 500 parsecs away from the Earth. And the other thing is a highly extended faint object, the galaxy. Now, as part of the 60F survey, a spectrum was taken of this object that included light from both sources. And here you see the spectrum in green. And the blue vertical lines mark spectral features that belong, in this case, to the star. And a comparison spectrum is shown in red of a star of roughly the right type that produces these absorption lines here. Now, funny enough, I mean, people know the magnesium doublet absorption line, but if you look at the object spectrum, it looks like there's a magnesium emission line here between the doublet. You would have never seen this before and wonder what the hell is going on. What is going on is that this is actually the O3 line from a slightly redshifted galaxy. Here is the complete set of emission features from that galaxy that is in the background of that star. So blended spectra affect more than 1%, less than perhaps 5% of objects in the sky, and are sometimes a problem. Moving on, let's talk about photometry and the sort of errors that we get in photometry. So photometry is essentially counting photons in a part of your image and then transforming it into a flux based on your calibration process, whatever that involves. But your calibration process is not perfect. It will come with an error. So for bright objects, it doesn't matter how many photons you actually collect. Your calibration accuracy will always be a limit to how precise you know the brightness of an object at the very bright end, independent of object brightness. And then at some point, when you go fainter and you've got fewer photons, the Poisson noise on the photon count from the object in question will take over, be larger than your calibration uncertainty, and will drive up the error as you go fainter. This is usually the domain in which work on Milky Way stars is going on. You're usually limited by the statistics of your photons from the star. If you go even fainter, where most of the galaxies reside and most of the AGN, they are actually fainter than the night sky emission itself. And you, of course, have to subtract the background before you can estimate how many photons you actually have in the object. And then it's not the photon statistics of the object, but it's the photon statistics of the background that dominates. And these two just have a different functional dependence. Over here on the right, this is taken from the SkyMapper survey. Again, you see an illustration of what this photometric error versus magnitude distribution typically looks like. Right, now, so let's talk about magnitudes. Magnitudes are, of course, an old-fashioned astronomical unit, which is a logarithm of a flux, of a physical flux. But we can measure the flux or the magnitude on different parts of an image. If you have a point source, it's very easy. You just want to know how much flux is in that source. And typically, the point sources in any one image will all look similar. So you have a point spread function that'll be characteristic. And once you've measured its shape, you know that all your stars will have a light distribution of a similar shape. You know where to extract your photons. You can do that in apertures, smaller and larger apertures, nested apertures. So you could have a sequence of growing apertures in area. And what you would find is that flux increases, obviously, because you add more photons from the wings of the PSF. And eventually that saturates. And then, you know, we call this a growth curve. Then, you know, you've captured all the flux. And basically, the total flux of the object is where you converge. Now, you don't always have to use nested apertures. If you know what the shape of the PSF is, any one of these apertures would suffice. You measure it just in the smallest aperture. And because you know the fixed shape of the PSF, you can extrapolate from that aperture just for the photons that you have been missing outside of the aperture, and you get an aperture corrected magnitude. So in this case, with this growth curve of the isolated star, that's what we've done here. And you basically get always the same answer, just wiggling a little bit with noise. And then an improved version of doing photometry for stars is so-called PSF photometry. So you think you know what the PSF is, you've measured it from the many stars in the image, and you basically fit that functional form, that shape, to your distribution of photons on the pixels, and you get a very accurate, the best possible measurement of how many photons have really been arriving from the source. But this only works if the source really is a PSF, is a point source. If you have an extended source, then this is plainly the wrong model, and with every model fitting, you will get a nonsensical result. So here we have an example of a galaxy plus a star in the foreground overlapping with it. And you can see, first of all, this growth curve is steeper, even though it comes from the same image, has the same PSF, because the galaxy is more extended than a PSF. So, and this doesn't converge so quickly. The galaxy's outskirts are actually fairly large. And if you try to do that correction for the PSF losses, you don't get a constant line, but you keep getting a brighter and brighter signal the larger an aperture you consider. And the PSF magnitude from that fit is completely wrong and meaningless because the object has the wrong shape. So for galaxies, for extended sources, what is most often done is a Petrosian magnitude, and that follows a particular definition. Basically, what happens is we average the light profile azimuthally of the galaxy. It's concentrated in the middle, and then it falls off to the side. You don't know how it falls off because every object is different. So you don't know it a priori. You have to measure the fall off for the object until you have so much noise that you can't follow it anymore. But what is done with the Petrosian magnitudes is basically you define a particular perimeter curve where the light profile has fallen off by a certain factor relative to the average surface brightness within that radius. And then you say, I don't know what's out there. I'm missing something. I don't know the reality and complexity of this galaxy's outskirts, but I am measuring this inner part to a certain level of fallen off brightness, and I know what the brightness inside of that is, and that's what we work with. And hopefully what I've been missing on the outside makes some difference from object to object, but maybe a difference we can ignore for the type of work that we are typically doing. Moving on and talking about spectra and extracting spectra. So let's first talk about slit spectroscopy, and in a moment we will talk about integral field units. So slit spectroscopy is the most common form of spectroscopy. Exists also in multi-slit units where you can observe multiple objects within a smallish field of view simultaneously. Here you have a bit of a trade-off. I mean, this object looks like it's got constant brightness everywhere, but really it's a PSF again, where most of the photons come from the middle, and then the outskirts are faint. You could choose a wide slit, or you could choose a narrow slit, and there are trade-offs. So with the wide slit, you get all the light from this PSF, including in the outskirts. So you get the right kind of total photon count. But you get a lot of background light coming through the slit as well. So that makes the spectrum noisier. You can reduce the background by a certain factor by squeezing the slit together. And you'll lose some light from the interesting source, but only a small fraction, because what you're clipping off from the source is here the faint wings of the PSF. You're holding on to most of the light in the middle, and you're reducing the background light by a much larger factor. So this is interesting to get high signal to noise. You just need to understand that you don't get all the light, and in some situations that could be problematic. For example, our atmosphere has the not very useful property that it actually refracts light. And so wherever at the sky we look, the sources are not really point sources, but they are extended by the atmospheric refraction. So their red light, their green light, and their blue light is centered on a different location. And it has a different degree of spread because seeing is wavelength dependent. So if you have a situation like this with a narrow slit, you run into the problem that the fraction of blue light you get in the spectrum ends up being different from the fraction of green light, and so on and so forth. So this can be really hard to calibrate. The advanced technology in this space is integral field unit. It's a lot more expensive because you're also using much larger detectors with lots more pixels to observe still a small number of objects. So basically what happens is you get a 3D data set. You get an image of a certain region of sky for every wavelength. That is, however, very interesting for the question of calibration and optimization of signal to noise, because you could be observing a galaxy here, and you don't need to make a decision at the time of observing about using a narrow slit or a wide slit. You have all of this light here in your 3D cube, and you can go into your data and define the slit or an aperture right in here. And you can do what you want. You could emulate a slit. You could use a round aperture, an elliptical one. You could play around and see what's most appropriate for your object. You could use an elephant-shaped extraction aperture. It's all possible because you have more data than you need, and you can play all the possible games. So this is the best of all worlds for both calibration purposes and high signal to noise aims. We need to briefly talk about calibration as such in optical astronomy. We have so-called standard stars in the sky, of which we believe we know exactly the photon rate that they emit, because great effort has gone over decades into measuring these standard stars very carefully. Initially, they used to be very sparse. And what used to happen is, anytime you observe an object you're interested in, you point to the object, you get your image on which you will do your photon counting, and then you point to the standard star, and you'll get another image and do the photon counting, and then do the ratio of fluxes to calibrate your target. That's fine if the weather is absolutely perfect. That's a problem the moment you have a bit more haze in front of your standard star than in front of your target, or the other way around. So there are uncertainties introduced by that. Now, nowadays we have the advantage of having the Sloan Digital Sky Survey, the SkyMapper Southern Survey, Gaia, sort of half sky or all sky catalogs that have really carefully, not quite as carefully as in the case of the proper standard stars, but rather carefully still measured the brightnesses of millions of objects. And so almost wherever you look, you have a magnitude standard in your image already that you can use from pretty much sources like Gaia, SDSS, and SMSS. With spectroscopy, it's still a little more complicated because we don't have already catalogs with billions of spectra in them. So you don't always have a spectroscopic standard in your field of view. You normally don't. So with spectroscopy, we are very much in this situation that we're still going from target to standard star, and we're suffering the consequences of having different throughput in the atmosphere. And the atmosphere is in particular highly variable, temporally variable and spatially variable in the U-band and at the UV edge of its own transmission. So if you observe sort of around 400 nanometers or shortwards, a spectroscopic flux calibration is still really, really difficult today. So I'd like to move on to data sources from Australia for any collaborative projects between Australia or Germany. Should we, Thomas, what do you think? Should we invite some questions now, or should I just carry on and we collect it all at the end?
Maybe if there's some quick questions already now, we can take them. Otherwise, we'll ask again at the end. Any questions at this point? Comments? Mara?
Yeah, thanks, Chris. I was going to say that I have nothing to learn about your lesson, but I was wrong, and I'm happy to be wrong. I was thinking to the calibration flux that you do in spectroscopy, considering the problem with the wavelengths that you were mentioning, where the blue, the green, and the red is absorbed in a different way depending also on the sync. Can you quantify the percentage of error that is done as a function of wavelengths?
It really depends on your instrument. and it depends on your setup. So for example, some instruments have atmospheric dispersion compensators that really work against the spatial offset of the objects. So you remove that problem. You would still have the problem that if you put the slit relatively narrow, that the different seeing spread among the different wavelengths would cause you problems. And that depends on how far to the blue you go. That really explodes into the ultraviolet, into the near ultraviolet. So say if you do a spectrum from 500 to 900 nanometers, the problem is not very large. Maybe you have a 10% or 20% problem. And if you already have photometry of that source, you could correct the spectrum just using the photometry, basically bending the spectrum back to the shape that you know it's supposed to have. But when your source is variable as well and your photometry is not taken, say, on the same night or something, then that's a problem again. But if you push to something like 350 nanometers, the problems with the problems can explode by how much you get the fluxes wrong. And it could be anything, depending on really what you do in your instrumental setup or what the people have done, whose data you are using.
Thanks.
Okay, then I suggest, Chris, you can continue.
Okay. So on the AAL website is a list of so-called participating surveys in the MOU between AAL and eROSITA. I'll just flash up 8 of them and tell you this website exists and contacts are being mentioned if you want to find out more and email specific people. The more important thing to say is there is actually more Redshift catalogs, both public and proprietary, than what this website suggests. And it takes a bit of contacting people to find out what else is there that they are happy to collaborate about. I mean, for example, we in our group are totally happy to collaborate about things that we have observed and may intend to still publish, but haven't gotten around to do so yet. There's nothing we plan to keep private forever. It's often a question of practicality. And I'll just quickly run through a few examples. One is, this is of course a public data resource, the 60F Galaxy Redshift survey that was observed about 20 years ago, 125,000 galaxy spectra from the Southern Hemisphere. But what our group has done is worked on fitting most of these spectra, and especially all of the emission line galaxies, to find particularly the type 1 and type 2 AGN, and to visually eyeball them all and confirm that our fits are good and that our classification is correct. One of these papers is submitted, the other of these papers is published. Then there is the S7 survey that was focusing on really nearby Seyfert galaxies, redshift less than 0.02. It didn't do all of them, it did 130 objects. We've extended their work to now just over 600 type 1 Seyfert galaxies. In fact, all type 1 Seyfert galaxies that we know of in the Southern Hemisphere. And we believe this is a complete set, at least as far as the 60FGS parent survey that tried to take a spectrum of every galaxy, except for exclusion zones, has observed would be complete. And we have a handful of Seyfert 2 spectra. So the difference is these spectra would now only be 1, 2, 3, 4 years old and would be more up to date because AGN also changed. One survey that's also only partially public at this point is the Allbright survey that aims to really get all the bright, meaning brighter than 16th magnitude quasars in the sky, both southern and northern hemisphere. You see a bunch of objects in blue in this diagram. So they are focusing on the most luminous quasars in the universe, brightest objects in the sky, as I said, and we have roughly double the sample size by now relative to what is shown here. So they are particularly useful if you're interested in high luminosity things. I'm going to skip that in the interest of time and mention that there are some very large extragalactic surveys that have been done over the last decade or more, based with instruments in Australia. but I'm going to defer to Simon O'Toole's talk, who will talk about Data Central later today, and show us how we can access this data. There's also a big survey that has been done for stars and their spectra with high signal to noise detail on absorption lines of quite a range of elements, but I will defer to Sven Buda's talk to talk us through that. Just briefly, 1 million stars with high definition spectra. And then there have been efforts to do integral field unit surveys of entire galaxy catalogs. For example, more than 3,000 galaxies at redshift less than 0.1 in SAMI. And then the currently ongoing project is Hector, which aims to do about 15,000 galaxies at low redshift again. And that's in progress. So I want to now go on and just as a last piece, talk about some problems that you encounter when you look at spectra or catalogs, and mention how it could be problematic if you use the public data blindly without questioning whether it is actually correct or not. We talked earlier about the problem of blended objects. Here in 60F, you often get the problem, and you get this also in some other multi-fiber surveys, when two fibers are next to each other on the detector, at the detector end of things, the light from one can bleed into the other. And then even though the sources are separated on the sky, and you look at these postage stamps and say, these are clearly just two single galaxies, they're not blended or anything, in the spectral data product, you end up seeing a blend of their spectra because instrumentally the light from their fibers was producing this crosstalk. So one of these galaxies has its own set of emission lines, that's the black one, but how it appears in the published data product is as a blend between its own light and a little bit of light from the much brighter fiber neighbor that has contributed extra lines. And this can be a confusing situation. Then anytime you have a resource where automated redshift fitting is done, you have to assume that in a certain fraction of cases, this is just going to go wrong. So here we see 4 examples where for 60F, it was reported that these 2 vertical lines mark the H beta and the H alpha line. And basically, they can sometimes completely confuse it with other lines, even though the wavelength ratios are not even correct. Or you can be looking at really problematic data, but the automated algorithm has fitted something. I'll skip over the Chen et al. 2022 catalog, which has a lot of problems in this way. You can ask me later if you're interested in that particular, but it's got about 50% of its entries wrong. Now, this sort of stuff, it's not a problem that only happens to beginners or amateurs. This happens in, headline data products that we use every day. For example, SDSS-DE 16Q, right? Many people on this call probably have heard of that resource or have even used it already. Last year, we wanted to publish a paper of the most luminous object in the universe, and the referee says, I just checked DE 16Q. There are several objects that are more luminous than yours. What are you talking about? And we were alarmed and looked at them. And here we go, redshift 4.1, the most luminous object in the universe, allegedly. You look at the spectrum, there's no way that this is at redshift greater than 2. Same here, allegedly at redshift 5, there's no Lyman forest. This is an object at less than redshift 2, and the derived luminosities are wrong. This is just because the fitting of the spectrum sometimes goes completely wrong. In fact, this is a really harsh example now, but I'll qualify it in a second. In SDSS-DE 16Q, there are 65 entries with a redshift greater than 6. One of them is right, 64 of them are bogus. Now, redshift greater than 6 objects are rare, intrinsically rare. They are the fringes of the distribution, right? The bulk of the entries in DE 16Q will be totally useful. It is always when you go to the highest redshift, highest luminosity, highest this, lowest that, into the fringes of the distribution, there you will see the mistakes piling up, even if normally the mistakes are a couple % and you don't really care for statistical analysis. This also happens to the most modern of spectroscopic surveys, DESI-DR1. Honestly, the first 2 spectra from DESI-DR1 that we looked at because our own spectrum was too noisy, and then we realized, oh, look at this, DESI-DR1 has a spectrum. Why did we bother taking one? Have wrong redshifts. So this one is supposedly at redshift 1.6 from their automated pipeline fit, but we fit it at redshift 0.89, and we are convinced that's the right interpretation. Or in this case here, it was assumed to be a redshift 0.18 galaxy. Maybe these lines here were assumed to be the calcium H and K absorption, but really you see quasar emission lines, and you also see 4 high redshift foreground absorbers, iron and magnesium absorbers, and this thing really is at a redshift of 2.36. So I'll stop here with the contribution that was meant to be fit before 5:40 Australian time. I don't even know what time we're at. Thomas, how are we doing?
Minus 4 minutes. So it's 5:44.
Okay, minus 4 minutes. So I've eaten into Chris Onken's time. Chris has given me a few minutes of time to talk about one aspect from his contribution's title. Is it okay if I just crack through that and then hand over to him?
Yeah, sure. If that's okay with Chris Onken, no problem.
Okay, so Chris will talk in a minute, 3 minutes, to you about the SkyMapper Southern Survey and how you can access its data rather more professionally than what I'm going to show you. I'm going to show to you the access through the website, which I prefer to do when I just want to play around with a thought or see what we know about an object. If you want to do some serious query for larger samples and serious amounts of data, Chris will show you how to do this a lot more effectively than using the website. But I'll do that first bit. So we've covered about 60% of the sky with the survey in 6 filters, and we have a web page on which you can do a cone search, and you can do image cutouts and various other things. For example, you could be looking for a specific object you're interested in and just check what does SkyMapper know about this. So either a SIMBAT compatible name or a coordinate, and it would produce a list of objects with separations relative to the coordinate you requested. And then you can click on the object viewer icon for maybe the first object. And then you're presented with this object viewer page, which doesn't fit on my screen. So I've split it into 2 parts with some overall information, some information about redshifts we know about, and then various different photometry entries from different dates when we observed the source, also Gaia cross matches and some multi-wavelength cross matches. And here you see a preview of the object in different filters and can get a fuller list of all the images with certain specifics for the object. Some of these objects are variable, right? This is an AGN, a well-known Cepheid-1 galaxy. You see here the core is brighter and the magnitude expresses it. It's 1.5 magnitudes brighter here than 2 years later or 4 years earlier. You can also query the overall database with an ADQL query. And then you get, again, a list of objects that fulfill your query, and you can potentially bring up the object viewer for some individual objects you're then interested in there. When the spectroscopic data that's available is from 60F or from DESI, you will see a little icon that leads you to a spectrum viewer. We just use the DESI's own spectrum viewer, and basically this links to the DESI page. So that's where you're then being taken. There's also information on the website about the tables that we have, and the table metadata here is the list of all the tables that are arranged in the database. And for each one of them, you will get an explanation of columns and so on and so forth. So that's the end for me.